So, hello everybody. Today I will show you how my colleagues and I used graph theory to explore neurocognitive interaction between language and memory. In order to explain why we decided to use graph theory, I will first show the framework of our study. Well, in contrast to standard localizationist paradigms that suppose that there are highly specified regions that are indispensable for a given function, we based our study on network paradigm that proposed that cognitive functions are based on widespread cortical networks, such as resting state networks or language networks. This paradigm also proposes that specialized regions are grouped into modules. However, just a collection of specialized regions won't provide for a coherent experience. Therefore, this paradigm highlights the importance between the communication between the regions within a module, but also between different modules. It was also proposed that regions can dynamically shift affiliation to different modules depending on the demands of the environment, so to adapt to the task. This idea of networks echoed from neuroscience to cognitive psychology, and it shifted the interest from studying the separated cognitive functions towards studying their interaction. So there is a growing number of research that explore how different cognitive functions interact in order to support our everyday behavior. Well, one of such behaviors that we are interested in is communicative behavior, specifically how language interacts with other functions to support it, especially declarative long-term memory. So now, what are the examples of this interaction and what is the evidence? Due to time limitation, I will just say that there are different studies that show the evidence of their interaction, coming from bilingual studies, developmental studies, anatomical studies, showing that these functions share some white matter paths. However, one concept is useful to show the interaction between language and declarative memory, and that is common ground. When we talk, when we communicate with someone, we formulate our message based on what we think the other person knows or thinks. So when I'm giving this talk, it will be different if I'm giving it to lay audience or to specialists as yourself. So we, communicative partners, rely on common ground or knowledge shared between them. And so we can see how language needs declarative memory, therefore as support, to perform this function. In memory research, we know that hippocampus is a structure that supports the integration of the information. And this structure has not been part of standard language networks. However, research in patients with hippocampal damage have shown that these patients, in addition to different troubles with memory, also have problems with language. These and similar studies led to the proposal that the hippocampus can serve as interface between language and memory, and that actually it is the structure that supports rapid access and integration of the information that language relies on when we communicate. Within our research group, we use one neurological disorder to study as a model to study this language and memory interaction, and that is temporal lobe epilepsy. There are several reasons for that. First of all, the epileptogenic network of these patients is centered on temporal lobe, that is the crossroads between language and memory cerebral networks. Also, these patients often have hippocampal atrophy or different patterns of cell loss within hippocampus that we saw is proposed to be the interface between language and memory. Due to insult caused by epilepsy, they often show cortical reorganization within their functional networks. And finally, they have different language and declarative memory deficits. So to sum up, our idea is to study dynamical interaction between language and memory to see how it supports our everyday behavior. To do so, we study its joint cerebral network, and we use temporal lobe epilepsy as a model for studying this interaction. Now, the question is, well, how can we study a network that is so complex? And this is where graph theory comes into play. So you saw already, explained by Sophie, what is a graph. I will just briefly recall. Graph is simply a collection of elements that can be regions or can be nodes, called nodes, and their pairwise link or edges. This can, in the most simple form, be represented as a correlation or adjacency matrix. Graph theory is a mathematical approach to modeling the connection between these elements. So to model the network. A network can be anything from how countries voted during Eurovision Song Contest over social networks to brain networks. And we saw graph theory as useful for our questions because, as you saw previously, it provides different measures. It can tell us, it can quantify how the network is functioning, and it does so first on the level of the whole network, but also, as we saw importantly, it can also tell us about specific node. But what is important, it's not just the node, but how node behaves, taking into account all the other nodes. Also, using this approach, we can study the network topology of different groups and see where the abnormalities of connectivity, such as in different neurological disorders, that we are interested in. So, from this neurocognitive neuroscience perspective and using network perspective, we posed as a hypothesis that this joint language and memory network is dynamic and that it changes depending on the state, meaning whether it's an intrinsic state or resting state without any activity, or if it's intrinsic state or task. We also hypothesized that it differs, it reorganized depending on the condition, whether it's a healthy individual or an individual with neurological disorder. To that end, we studied healthy participants and temporal lobe epilepsy patients who performed fMRI protocol that consisted of resting state that we used to measure intrinsic activity, so without any task, and recall task in which that was used to measure extrinsic activity. During this task, we asked participants to recall and repeat the sentence they previously generated. So we explicitly asked them to use language and memory jointly. We compared resting state and recall task in order to see how is network reconfiguring. So what is the network trying to support with its adaptation? What sub-processes? And we also compared healthy participants in temporal lobe epilepsy patients to see what are supplementary processes that the network is trying to support through its reorganization. To do this, we used graph theory. We were specifically focusing on modularity. So we had 19 control patients and 60 temporal lobe epilepsy patients doing a resting state as measure of intrinsic activity and recall task as a measure of extrinsic activity. We defined our joint language and memory network previously based on 2 meta-analyses, and then we translated them into the space of wide resting state networks. For each region of interest, we then extracted time series, and we created correlation matrices that you saw previously in Sophie's presentation. So in these matrices, each row and each column represent a region, and the cell represents the correlation of their time series. Using these correlation matrices, we performed then a community structure analysis to see how these regions segregate into different modules. Importantly, we wanted to see not only how they communicate within module with this intramodule connection, but also between modules with this intermodule connection that actually allows for integration. And using these 2 parameters, how a region communicates with other regions in its module, and how it communicates with other modules, we can define different roles. In our case, we used 4, and the most important for us here is connector hub, which are regions that are highly connected within its module, but they also connected with the other modules, providing for integration. And here are our results. So here, you can see on each side modules during resting state and recall. And these rivers show how their composition changed. The number here represents a reconfiguration parameter where we calculated how many regions changed their affiliation. So what we saw in healthy participants, interestingly, is that when moving from resting state to recall, there was a segregation of temporal mesial nodule composed of temporal mesial regions, as it similarly to what was predicted by previous studies, and also even more so because the regions in this module had mostly integrative role. What was also interesting is that modules who had the highest reconfiguration were temporal limbic module and this pink frontotemporal-parietal module that actually were composed of key language and memory regions. So the reconfiguration from resting state to recall, from intrinsic to extrinsic in healthy participants was marked by a movement of key language and memory regions. However, in temporal lobe epilepsy patients, we saw different pattern of dynamic reconfiguration. First of all, when moving to recall, they had higher segregation, meaning more modules. There was no segregation of this temporomesial module. However, there was a segregation of insular cingulate and temporoparietal regions that were mostly composed of regions belonging to control attentional networks, suggesting that they were processes that they needed more to, that they needed more. What we also saw was that this temporal limbic region had a reduced reconfiguration or reduced flexibility. And what was also interesting, we were looking what was the distance between regions within module, and we found that during recall task, patients had more smaller distances between regions, meaning that their modules were more closely together. Now, when we focused on the roles, we saw that when we observed connector hubs and their change from rest to task, we saw that patients had more connector hubs in this control network, control and intentional networks. Also, when we analyzed hub disruption index that you saw previously, we saw that there was indeed disruption in this integration property, so how nodes can connect with other modules, and temporal lobe epilepsy patients had lower this property in both during rest and recall. And then we analyzed that on the nodal level, so to see how each of these nodes, what was their property to integrate their integration property. And what we saw was, we actually found this interesting hippocampal paradox that was previously described in literature, meaning that during resting state, hippocampus and mesial structures have increased integrative property. However, it was proposed that it is not functional and that is due to epileptic discharges. And indeed, when we checked the task, we actually obtained that these regions had reduced integration property, meaning that this high integration property of hippocampal structures during rest was not functional. So to conclude, in healthy individuals, language and memory network reconfigures through migration of key language and memory regions, and there is also segregation of temporomesial module that can act as an interface between language and memory. However, in temporal lobe epilepsy patients, the reorganization is evidenced through higher segregation, which can be explained in different ways. It can be that it supports functions that they need to overcome the lack of interface, or it could be due to loss of distal connections in temporal epilepsy, or it could be to prevent from damage propagation through network. Then in our research group, we used results such as these ones to propose different models of language and memory interaction that I will not now go into detail. What I wanted to show you today is how graph theory can be useful to study questions like these. First of all, it's interesting because if we're analyzing modularity of a network, we can see what are the processes that are needed, that are supported through network segregation, but more importantly, how they're integrated, so how these sub-processes are connected. Also, we can study not only the behavior of the whole network, but also the behavior of each node, but not as separated, but within a network, with a relation how it interacts with other nodes. And this allows us to study cognitive networks and their underlying cortical networks. Now, here I've only presented how we can study cortical networks, but in our research group, we indeed use this approach for other functions or other neurological disorders. What is interesting is that here we used fMRI, but you can use with other measures, such as neuropsychological tests, and you can even use it you can even use participants as nodes. So, for example, you can study how a group interacts and what are the connections between them. Thank you very much.